talk to everybody. This is the first talk in the first conference in what we hope will be a series. 3 of the conference, the series are already set up. This is the Majorana. Next one is the quantum, which is a very big one, covers all of what these days are called quantum computing, quantum information, quantum algorithm, quantum emulation, very broad. And the one after that is called twisted. That's mostly on this twisted, strongly correlated graphene and other materials. And we'll continue. There'll be many. And basically, the conference series reflects my interest in physics, okay? So I told all the speakers, and this is the instruction to myself also, that the talk should be aimed just at me. So the talk that you will hear today from me is the talk that I prepared for myself. Of course, others will be listening. And the series is named after Janet Sarma, who actually kind of created CMTC. She was the only administrator we ever had. And, you know, I mean, of course, nobody knows who she is because she was always behind the scene. So, and she'd have been extremely angry if she found out that a conference has been named after her, but she doesn't get a vote. All right, so let me start. Searching for topological Majorana zero mode. This is what everybody wants, and this is what we all want. Majorana zero mode is a very exciting object. And this search has been going on for a while, and I'm going to give you my view of what the journey has been like and where we are, but I'll do that in some depth. So I'll skip certain things, but whatever I discuss, I'll discuss in some depth. I'm not naming my collaborators right in the first slide because I could not even finish counting. It's easily more than 30. I stopped at 30. You'll see the names in the talks, not all the people I collaborated with, you know, work will be represented. Also, I'll restrict myself to semiconductor, superconductor, hybrid nanowire system in this talk, covering the period 2009 to 2021. There are many other platforms in which Majoranas are being searched for. And in fact, the other 7 talks today will cover some of those other platforms. The ones I think are the most interesting, most exciting, and the most, I would say most hopeful in terms of success. But you know, it's reflecting my taste. So if I do not have your favorite platform, I apologize already. This conference is really for me, okay? All right, so this is the first experimental paper. Search involves experimental work. When you're searching something, theories can only predict or try to understand, theories cannot search. Physics is an experimental science, so this was the very first experiment that claimed signatures for Majorana mode, you know, signatures. So these are kind of terminologies that these glossy magazines like. Signature, evidence. Signature, I think, is a bit weaker than evidence. An observation is a bit stronger than evidence. These are things I recently learned. This is the very famous paper from Leo Cohn-Heaven's group, Maurik et al. In Science. And what you are seeing is tunneling conductance plotted against bias voltage. And as each line presents a different magnetic field, and usually in superconductor, nothing good happens when you apply magnetic field, right? In a superconductor, apply magnetic field, everything just disappears. But the prediction was, as you apply magnetic field, you will see something, and as you can see, zero magnetic field, not much is happening. Then at finite magnetic field, a zero bias peak emerges, and this zero bias is presumably is a signature for the Majorana mode. So this goes all the way to, you know, this is like 500 millitesla, half a Tesla. Science 2012. I am showing in this first slide the 4 most important experiments in my view. The next one, and I have been very even-handed between Delft and Copenhagen. The next paper is Deng et al., Science 2016. And to me, the breakthrough here, this has 2 breakthroughs. This was the first breakthrough. This showed the experiments are possible. The thing that theory predicted can actually be done in the lab. You know, not everything theory predicts can be done in the lab, but this can be done in the lab. So it's a very important experiment. Never mind signature or not. The next experiment, next important experiment, 2016, from Copenhagen, Deng et al. Showed very nice zero bias peak, as you can see here, very sharp peak. And also it found a hard gap. See, the gap is very hard at 0 Tesla. Here, the gap is very soft. So it's a huge improvement from here to there. Huge materials improvement. Hard gap, very nice peak, very sharp peak. Here, the peaks are not so sharp. Next, also in 2016, Nature. I have been even-handed not only between Delft and Copenhagen, also between Science and Nature. Nobody can be mad at me. So here is the Nature paper, also from Copenhagen. If you don't know what Copenhagen is, this is one of the two groups in Copenhagen. Second group is represented in this series. This is Charlie Marcus's group. So here the claim is that they have seen the exponential protection. This is not an experiment I'm going to discuss in details because that's going to take a very long time. But the claim is that over here, this splitting, when they do it for different wires of different length, they see something exponential. I think that claim is incorrect, but it's a very important experiment, not because of the claim, but because of the fact that it showed that Coulomb blockade and Majorana physics interplay with each other, and Coulomb blockade can be used effectively to study Majorana physics. The claim is correct. And the experiment saw both E and 2E effect. 2E is the Cooper pair, E is ordinary electron or Majorana mode. We don't know, both of them will have E. So it's a very important experiment. Then the famous 2018 Nature paper, which has just been refracted. So that's why Nature is an inverted quote. Their beautiful zero bias peak is seen, and this peak even has height 2 square over h. Now we know the height is actually slightly above 2 square over h. Not precisely at 2 square over h, but it's very sharp peaks. I would say these are the best peaks that have ever been seen in the Majorana business, okay? Very nice zero bias hard gap, zero field hard gap, and very sharp peak, okay? So these are the 4 important experiments. And what I want to tell you that all of these highly demanding, difficult, ambitious experiments, these are very difficult experiments, okay? Claiming signatures, this one claims signature of Majorana, this one claimed Andre bound state, this is Andre bound state becoming Majorana bound state, this claims exponential protection, this claims Majorana quantization. They all suffer from decisive confirmation bias. Theory told experimenters exactly what to look for. And there are sufficient number of tuning parameters in these very complicated experiments. And if you tune them, you may convince yourself you have seen what the theory is predicting. This is a price to pay in this field. The field is theory driven. Experiments are extremely complicated. Very few groups can do it with lots of tuning parameters, and there will be confirmation bias. There's nothing wrong with that, and eventually we'll get to the truth. So, we have no standards for claiming discovery in condensed matter and AMO physics. So anybody can claim discovery. You are limited only by your conscience and by Nature and Science and these glossy magazine editors. If you claim a discovery in some physical review B, nobody's going to pay attention, right? So you can claim discovery right and left there. But this very big discovery, which attracts attention, suffer in these difficult experiments from confirmation bias. There is nothing wrong with that. It's just that we have to sort them out. Let there be claims which may not quite pan out. So what? It's still advanced. So, I want to emphasize this, that confirmation bias is not necessarily bad, because advantage of confirmation bias or advantage of big claim is that lots of people come and start working in the field, and if the claim is not quite accurate, it's going to get sorted out. So what is the confirmation bias here? Theory actually predicted. This is a paper not very highly cited, Jaideep Sahu's work. These are all very well-known people now, first 5, but they were all amazingly postdocs at Maryland in this Condensed Matter Theory Center during 2008 to 2012, an amazing period of productivity for this group. And in this paper, I don't know who drew this picture, probably Jaideep. We actually told what the experimenters have to do. And then the experiment is exactly like this. We said STM, what we made a tunneling probe. We thought of STM, but a tunneling probe. We said, take a nanowire. We even said what nanowire, indium antimonide, indium arsenide. Put it in a superconductor. We even told the experimenters what superconductor, aluminum or niobium. Apply a magnetic field. And then we said that if you do that, at high enough magnetic field, there'll be a topological quantum phase transition. As you increase magnetic field, the S-wave gap induced this nanowire will come to 0, because magnetic field, this is the Pauli blocking, the Clarkson-Chandrasekhar limit. But we said because of spin orbit coupling, what would happen is that once the gap closes, if this was just a pure S-wave, nothing else would happen. But here, a new gap will open, and this is the topological gap. This is a spinless, effectively a spinless PUF superconductor. And for different values of spin orbit coupling, these are all different values of spin orbit coupling, this gap will be proportional to the strength of the spin-orbit coupling. If spin-orbit coupling is very large, like 0.5 electron volt angstrom, you'll have a very large gap. This is a gap of something like 5 Kelvin. And then the gap will slowly go down. So this is what experimenters are looking for. And we even showed what they will find if they measure conductance in this tunneling. We said if the applied magnetic field is 0, you will just see a gap, nothing, no peak, right? This black line, dashed black line. That when at weak magnetic field, all that would happen, the gap will shrink, which is what happens. So if you look at this red line here, the gap just shrinks. But at some field, you will have a topological quantum phase transition for this green line, and you will now have a smaller gap. This is the topological gap, and you'll have a zero bias peak. So this topological gap and the zero bias peak always come together. This is the famous bulk boundary topological correspondence. And then is an increased magnetic field, this gap will change. Amazingly, in this original experiment, we did not make a big deal of T score over H, although we knew about it, because I wrote a paper in 2000, 12 years before that. The reason is we knew seeing T score over H is almost impossible because you'll have too many parameters. You have temperature, you have tunneling barrier, you have dissipation. And so we did not make a big deal. We said you'll see a T score over H, you'll see a peak, and you'll see a gap. And we also said the gap will oscillate. This is as a function of the length of the wire, the gap will oscillate. It will also oscillate as a function of magnetic field in this region. Okay. So all the predictions are there, and this is what experimenters trying to confirm. By the way, these predictions have not changed. We now understand much more. We understand what disorder does to it. We understand what Coulomb blockade does to it. We understand what inhomogeneous potential does to it. But the basic predictions are these. This is what experimenters are trying to verify, often not citing this paper, by the way. The 2 PRLs that are cited do not tell you any of these things. Okay, they just say this system will have Majorana. So this is the confirmation bias. This is what experimenters are trying to find. And when you try to find something and you're very clever and the experiment is very complicated and you have lots of tuning parameters, sometimes you find them. Let me tell you, this confirmation bias is not a problem just for Majorana. It's a problem for this whole field of topological condensed matter and atomic physics that has dominated our subject for roughly last 20 years. So this is what topology used to be when I was younger, quantum Hall effect. You needed no prediction. Quantum Hall effect was not predicted. The fact that it's topological became clear over 20 years after its discovery. See, this is von Klitzing's original discovery. Absolutely horizontal line. The fact this is important was obvious right away. It was sent to NIST for refereeing because these resistances were quite precise. Well, now this is the standard for resistance. You did not need to know anything about topology to know this is an important discovery. In fact, I contend this is one of the 2 most important discoveries in low energy physics in last 100 years, more than 100 years. Kamerlin also discovery of superconductivity, and this is discovery of quantum Hall effect. This is fractional quantum Hall effect, original discovery. Sui, Stormer, and Gossard. There's no question there is something very amazing is going on. Okay, this is the discovery of the half fractional quantum Hall effect in a bilayer system. Okay, by Princeton and Bell Labs both. Okay, this may be, I'm not sure whether it's Princeton data or Bell Lab data. This is the discovery of the 5-half fractional quantum Hall effect. So all of these are obvious. You did not need any theory. There is no confirmation bias here. Now let's look at so this is all before 2000. Now let's look at, well, let me take the suspense out. Okay, these is original integer quantum Hall effect, fractional quantum Hall effect, half fractional quantum Hall effect, 5-half fractional quantum, or before 2000, 80 to 2000, what topological physics theory followed experiment. Then 2000 to 2020, experiment is following theory. This is the original discovery of quantum spin Hall effect. Well, people of goodwill could disagree, but I would say if the theoretical prediction was not there, this is not considered, this would not be considered a discovery. Because as you can see, this is quantized within like 50% with a lot of noise and over a very small region. I'm not sure that this would even be submitted for publication if the theoretical prediction was not there. Now, I'm not saying it's confirmation bias. This is most likely correct, but things have not improved much because this is not really protected totally, okay? This is what I'm trying to say. This is the so-called Majorana zero mode in Princeton work on one-dimensional ferromagnetic chain, there is no gap anywhere. These peaks are, this is not publishable work if theory did not exist. Nothing wrong with that, but I'm saying that the picture changed completely in between these two eras, because here theory now leads. Here is perhaps the most convincing one, quantum anomalous Hall effect, Chi-Kung Shu's work, original work. But again, look at how narrow the region of quantization is. Would it be this was 2D force work, took 5 years of material science to get here. But I'm not convinced that if the theoretical prediction was not there, this should be submitted. Well, the certainly would not look for it, but this would be submitted. And this, of course, is the famous nature retraction. I'm not going to talk much about it, and you know what happened here. Eventual recalibration showed that what was thought to be 2 is really 2.2. And since there is no prediction that Majorana quantization is 2.2 square over h, I insisted that we must retract the paper. There are people who are claiming on the Twitter that they are finding of various flaws, and those are very serious experimental flaws. But to me, this was the most important thing, that even if there was no data cropping or anything, this paper still would have been retracted, because the lock-in calibration was. Yeah. Somebody wants to ask a question? I cannot hear you. A lot of noise. Can you repeat? Can you repeat the question?
No, Shankar, I think it's just someone joining with unmute. I think there's.
Okay, all right. Okay, I'll continue. So so here again, it's not 2, it's 2.2. So confirmation bias played some role. So I want to emphasize that those who claim that this experiment, something was very wrong with those, those who are very, very busy on Twitter, literally have nothing better to do, 100 tweets a day claiming how great we are, they are missing the whole picture. The subject has changed. This is the era where experiment established theoretical topology. This is the era where experiment is changing theoretical topology. You must have confirmation bias here, because that's what you're doing. The Higgs mode was seen because Higgs predicted in 1964, and $10 billion or $20 billion are spent trying to see it. That is confirmation bias. Now, high energy physicists have an advantage. Their community got together. They can easily get together because the whole community does one experiment, all 10,000 of them. They got together and they defined what a discovery is, 6 sigma. We have no definition. If I do an experiment tomorrow and I somehow convince Nature editors to publish it, I have made a discovery. This bothers me a great deal. I think in this era of topological physics, we as a community should have some definition for discovery, but I don't think in our subject it's going to happen. But in any case, this is the problem. The problem is theory chasing experiment, extremely complicated experiment, okay? Trust me, these experiments are very, very complicated. And you spend like 2-3 years, you have many tuning parameters, you kind of see what the theory predicted, somewhat vaguely, okay? All right. There have been 43,000 papers between 2000 and 2020 on topological physics in condensed matter and AMO, mostly in condensed matter. 43,000, a mind-boggling number. Now, I have been thinking about Majorana for more than 20 years, okay? And I have looked at least 10 different systems and material platforms. So let me quickly go through them. So my first paper in 2000, which showed that this 2 square over h, this was in organic superconductors, Viktor Yakovenko. And then I did a lot of work on fractional quantum Hall effect with Michael Friedman and Chetan Nayak and postdocs at Maryland. Then I did work on Sloan-Seb Rutherford, which is supposed to be a P-wave superconductor. Then I got diverted into P-wave atomic systems. late Debbie Jean was doing some incredible experiments on P-wave gases. So I got very excited, and I wrote several papers on atomic gases, possibly trying to see topological superconductivity and Majorana mode, but that I don't think is happening. Then you switch gear after Jaideep Sahu and Roman Luchin came to Maryland. And I asked Jaideep to understand Fu and Kane's paper, and we realized that Fu and Kane, we are not motivated by Kitaev's work. We are motivated by Fu and Kane. We are trying to understand Fu and Kane, and we realized Fu and Kane can be created without a topological insulator, just with spin-orbit coupling and magnetic field. That's our original paper is 2-dimensional. Then, of course, he quickly realized that, so this is a paper on topological insulator, that it can be done in one dimension. More recently, I have been doing a lot of work on this iron-based superconductor, which we'll hear about today, but I'm not talking about that. So I basically worked on almost all the major platforms. I have a paper on ferromagnetic chains also, showing that probably Majorana has not been seen there, but it's a very interesting system. So, so I take my commitment to Majorana very seriously, perhaps more seriously than any other single individual, because I have worked on all the systems, and I think no one else has worked on it for 20 years, okay? But that does not mean that I believe topological Majorana modes have been seen. Let me tell you my belief. My belief is it has not been seen. We are very close to seeing it, and it will be seen. But I do not think it has been seen. I want to make that very clear. This talk will be posted on YouTube, and I want to make that very clear. I see no reason why it will not be seen, but I myself am not persuaded that anybody has seen it. So maybe I'll skip this slide. It's not so important for my talk today. Free Majorana is a neutral Dirac fermion, like neutrino possibly. That has nothing to do with what you're talking about. So people who say Majorana fermion are making a capital mistake. This should be really called Majorana modes, because these are non-abelian anions. These are zero energy excitation in a topological superconductor. But the important thing is that they are not fermions. Two of them together is a fermion. So they're kind of half fermion. So what happens is that they then they have a degenerate subspace, quantum degeneracy of 2, because two of them together is either a fermion or nothing. So this is a parity degeneracy. In a superconductor, only thing that matters is whether you have a charge or you don't have a charge, and that's the degeneracy. So 2n of them will have a ground set degeneracy 2 to the power n-1 that enables topological quantum computation, which is Alexei Kitaev's great insight in 2001, non-local parity, and this thing is non-local because in reality you cannot have a half fermion, so you always have one fermion. So you always must have two Majoranas. But those Majoranas are well separate. If you put the two Majoranas on top of each other, they're just an electron or a hole or nothing. But if they're very far from each other, they're real objects, and that's the Majorana mode you're looking for. Okay. Now you need 4 of them to form a qubit, and I'm not talking about qubit at all in this talk. So you need one Majorana first before you can have 4 Majorana. So superconductor has natural host for Majorana. This was realized early, Nick Reed pointed this out already in 1999, or even before in the paper with Moore. So what happens is that in a superconductor, as you know, Cooper pairs are not the excitations. Cooper pairs are the ground state. So what are excitations? Excitation is Bogoliubov of quasi-particle. It's a mixture of an electron and a hole in the gap. So a mixture of electron and a hole means it's already kind of a Majorana. So you have a linear combination of an electron operator and a hole operator, or electron operator adjoint electron destruction operator. So if you can make U is equal to V star, then gamma is equal to gamma dagger. That means then the self-adjoint, and that is a Majorana operator. So all you need to do is find a superconductor where U is equal to V star. And why is this magical? Why can it happen in a superconductor? Because in superconductor, Cooper pairs come for free. So you can change an electron into a hole by just adding a Cooper pair. This is why it allows you to construct Majorana in superconducting gap. But the problem is in ordinary SOF superconductor, you cannot do that. Because ordinary SOF superconductor, you have fermion doubling problem. So each electron comes with a hole. So you will not have a zero energy state at all. You cannot make U is equal to V star. To make U is equal to V star, you need a zero energy state, because this thing has to be exactly at zero energy, because each electron state comes with a hole state, an exact symmetry, electron hole symmetry. So only you can have an E is equal to 0 state is if you have a spinless POF superconductor. Now, spinless POF superconductor probably does not occur in nature. Maybe these iron-based superconductors are spinless POF superconductor. We'll hear about it. It's not clear, but let's leave that out for a minute. They don't occur in nature. Okay. So you have to form them. And we had an idea. This is the paper in 2000, in fact, as you can see. It was submitted to PhysRev letter in 2000, got rejected, came out in PhysRev in 2001. And we thought that certain quasi one-dimensional organic superconductors may have this property. And he wrote a paper, and there we said that these two edge states at the opposite ends are described by Majorana operators. This is taken from this paper. Majorana operators opposite parity. And since Viktor Yakovenko knew Alexei Kitaev, they're both from Lambda Institute, Alexei told him this is just the Majorana that he's writing a paper on. So Alexei wrote a paper in the same year. Both papers came out Alexei's paper came out 6 months after our paper, but he has been thinking about it for a while. And he basically had everything clear in his mind that he thought a lot, he thought a lot. He thought for more than a year for a physical realization and could not come up with anything. So he wrote a really beautiful paper saying, suppose you have a one-dimensional wire which is made of spinless PUF superconductor. Well, if you spinless PUF superconductor, there'll be Majorana modes at two ends, and if they're well separated, their energy separation will be exponentially small, and this thing will be an anion, and you can do topological quantum computation. Alexei actually put a lot of thought into whether this system can be realized in practice, and he concluded it's very unlikely. And in fact, in his paper, he writes, if you read his paper, you'll find there is a sentence saying spin-orbit coupling does not help. He came very close to what eventually became our proposal, okay? But he concludes spin-orbit coupling does not help. Anyway, we then realized that if spinless PUF superconductor does not exist naturally, it can be made in the laboratory using ordinary ingredients. Ordinary ingredients are nothing other than three ingredients, okay? A semiconductor, which is spin-orbit coupling, a superconductor, a SOF superconductor, which is superconductivity, Cooper pairs, and a magnet, which breaks time reversal invariance. If you combine these three judiciously, we showed that you'll have Majorana modes, an original proposal 2D. I told you we were really thinking about Fuan Kane, not Kitaev. I think our original paper, this paper did not even cite Kitaev because it's a two-dimensional paper. But this paper is the paper that had the idea that you combine these three, you get Majorana. Okay. Here, the Majorana, of course, will be in a vortex core or a running mode around. But it's very easy to go from here to, and we showed in this paper analytically that the Zeeman splitting has to be larger than chemical potential square plus the gap square root, and then you will have a topological PUF superconductor in 2D, and there you have Majorana from ordinary ingredients. Okay, and then immediately we realize more or less right away that converting into 1D to get what Kitaev dreamt about is straightforward. All you do is take this two-dimensional system and squeeze it. You get 1D, and then what happens? The Majorana gets squeezed at the two ends. The Majorana that was running around the edge, you don't need any vortex anymore. Any Majorana that was running around the edge, by squeezing it, you make just a bounce set, a defect set at the two ends. And we wrote a paper, and another group wrote a paper more or less simultaneously, I think 1 month after us. And this is the system everybody's looking at. Indium arsenide antimonide semiconductor, aluminum or niobium, and this is the Hamiltonian, and these are the original theoretical papers which predicted various aspects of it. You need spin-orbit coupling, Zeeman splitting, and then you need to put the gap at the right place. Once you put the gap at the right place, that is it. You're going to have Majorana. Okay. Let me just skip this. This is theory that everybody knows, and if you don't know, I cannot describe it in 1 minute. But you can do numerical work, and you find that there is, just by changing either the spin splitting, Zeeman splitting, or the chemical potential of a phase diagram, this is the topological region. In this region, the nanowire has become a spinless PUF superconductor. And the basic physics is very simple. This is when you have no spin-orbit coupling. This is when you have spin-orbit coupling. Well, spin-orbit coupling, the two parabolas shift. Now you apply magnetic field. You create a Zeeman splitting, two spins. So you have a spin helix here, spin structure. Now if you put a superconducting gap here, that's it. It's a single spin system. The spin is rotating like this, but it's a single spin system. So you will have a PUF superconductor here, which is effectively spinless. Very simple idea, actually. One electron band structure, always correct, never wrong. Here is some beautiful early numerical work by Tudor Stanescu. This is actual numerical work, not schematic. When the Zeeman splitting is larger than this quantity, you have Majorana. This is the two Majorana, two ends of the wire. These are 10 micron, and this is the gap. And when the Zeeman splitting is less than this, there is no Majorana. So this is the topological quantum phase transition at this point. Okay, either you have Majorana or you do not have Majorana. So this is the experiment that was done, the famous signature experiment. So the question now is, they saw this zero bias peak. And this is Tudor Stanescu, will be the last speaker today, his simulation. And this is what in 2012 was shown. So is this Majorana. And this was quickly reproduced by several groups, this experiment, right away, more or less, because many groups are looking at it. 6 different groups reproduced it. I'm not going to name all the groups. Here are all the, this is the original experiment. This, I think, from Weitzman. This is from Harvard, one of them is from Lund. All of them are here. One from Urbana. Just quickly reproduce. All of them have the same features. You get a zero bias peak at finite magnetic field. You get very soft gap, and it kind of looks bad. Looks like something you could not publish if the theory did not exist. But they all saw the same thing. So there is no question that people are getting zero bias peak in a nanowire when they apply a magnetic field when there is spin orbit coupling. The question of disorder was in my mind right from the beginning. So we did a very theoretical calculation, renormalization group calculation, which I'm not going to talk about. Both disorder and interaction question bothered me. And Alejandro Lobos did a 2D force RG calculation showing that weak interaction and weak disorder, because RG you can only do part derivative RG, weak interaction, weak disorder, all these things are stable. So everything I told you, free fermion theory is completely stable, even when you go to interacting fermions with some disorder, as long as interaction and disorder are weak. So that was a very important discovery, theoretical discovery, because if it's not stable, there is nothing to talk about here, but it's stable. But what about the soft gap? Where is the soft gap coming from? Obviously, it's a strong disorder effect. This also, we wrote a paper in 2012, and our prediction was, we did a lot of numerical work. Our prediction was the soft gap is coming from disorder at the superconductor semiconductor interface. So our prediction was that if you can make this interface epitaxial, then you will get a hard gap. Okay, this is our numerical simulation showing this soft gap gets converted into hard gap when you eliminate this disorder. So I remember Charlie Marcus calling me from Copenhagen, asking me, is this a real theory? How much do you believe it? I said, I believe it in totality. And that's when I first heard the name of Peter Koekstrup. Charlie told me there is a colleague of his in Copenhagen, young colleague, chemist, Peter Koekstrup, who knows how to make this epitaxially, and rest, as they say, is history. This is the important paper. It took them a couple of years. Chang et al., like many experimenters, they published one paper in Nature Materials and one paper in Nature Physics, basically from the same data, because it's aiming at different people. And I think Nigard is talking today. I do not know exactly what his role was here, but clearly it's important because his name is next to Charlie's. And this is theory. This is our paper. This is theirs. And this, I think, is one of the most important advances in the subject. Experiment followed theory, and we have now hard gap. Without hard gap, nothing would have happened. And look how the improvement, okay, from this to this, tremendous improvement, materials improvement. Without materials improvement, there is no condensed matter physics, right? Pentium chip happens because Intel put a lot of money in improving silicon. So let me just show you all the data. So this is Maurik Frolov, Science 2012, signature of Majorana. This is Lund. This is Urbana. This is Harvard, all 2012. All to Weitzman, all 2012. Well, I'll come back to this. Something else. This looks like 2012. This is the retracted paper, but same data done correctly now without any cropping and showing that is 2.2, not really 2. Anybody who claims that this and this are the same is just lying. This and this are not the same, lying or blind, right? You can see there's been huge improvement, very hard gap, very sharp peak. This and this are not the same. This is much better, much clearer physics than this. Now, let me tell you what this is. People who did this work, so all of this 1, 2, 3, 4, 5, 6, a tiny zero bias peak at a finite magnetic, very tiny, okay, like 1%, 2% above background. Peak height, very small, soft gap, superconducting gap, very weak always, with lots of subgap state, broad peak, no sign of gap closing opening, nothing happening with field except a tiny zero bias peak, no splitting of peak. And later on, I found out to produce even this peak, one had to subtract the contact resistance. Okay, so what is this? This is a paper that came out actually in 2021 in Nature Physics. I have no idea the rationale. And the claim of these authors is that this is the same as this. I completely reject this claim. This is not the same as this. This would have been a good paper in 2012. Okay. This is not a good paper in 2021. Okay. This is regression, not progress. This is progress. So there has been enormous progress between 2012 and 2021. This belongs to 2012. Okay, this should not have been published in 2021. All right. So why am I saying that even this is not Majorana? Okay, I'm saying even this is not Majorana. Why? There are many papers on it, but I'm going to talk about the paper I like the most, one of Haining Pan's work, and we call it good, bad, and ugly. Good is pristine Majorana. Bad is when you have inhomogeneous potential, and ugly is when you have a lot of disorder. Okay, so let me show you what happens. I mean, instead of talking, let me just show you the results of tunneling spectroscopy. Okay, so this is what the experimentalists do, and we actually did this work trying to understand the Nature paper before retraction. We concluded even before retraction, what Nature saw was not Majorana. Okay, this paper, which the work was done in 2019, already says that that was not Majorana, long before all these problems in the Nature paper were pointed out. I want to make that very clear. In all the hula baloo that's lost, that we were already on record saying most likely Zhang Nature 2018 did not see Majorana. That's this paper. Okay, so here is Zhang Nature 2018, which is retracted now, but the data remain the same. This data is not retracted. What is retracted? Retraction is based on other factors. And this is a very closely related paper from Copenhagen, Nichel et al., which also sees 2 square over H in indium arsenide system. These are the two experimental, as of, let's say, before the retraction, two claims of 2 square over H as close to Majorana as you can be. Both papers claimed this one more softly than this one. Majorana quantization has been seen. This is Haining Pan's best simulation getting agreement with this experiment. Agreement with quote unquote, okay? This is very good agreement. If I didn't show you which one is experiment, which one is theory, you'd not be able to tell me. But this is not good result. This is not pristine Majorana. This is ugly. This is created entirely by disorder. This has nothing to do with topological. The topological quantum phase transition point is somewhere over here. This is all below that. And it agrees so well. This is why in this paper, in 2019 work, we said that, these experiments are not seeing Majorana. Most likely they're seeing disorder. So this is the corresponding thing bad with inhomogeneous potential. And this is what good looks like. Good doesn't look like this at all. So already before retraction, we showed that disorder with fine tuning, most disorder results do not look like that. But if you do sufficient fine tuning, you find results which look like this. Now, let me emphasize, since I collaborated, I knew how much fine-tuning experimentalists do. Enormous amount of fine-tuning goes in because it's a very difficult experiments. Out of 80 samples, only 3 samples show some signal that you like, then you tune everything to get this result. Okay, this result doesn't rain from the sky like quantum Hall effect. Okay, so this is fine-tuned, this is fine-tuned. Level of fine-tuning is about the same, I can tell you that. Okay, so this is a theory. Either we have nothing, in which case it's the good, or you have an inhomogeneous potential, bad, or you have disorder, that's ugly. And Haining Pan can do all these calculations. Okay, he's very good. And this is good with a lot of chemical potential disorder, not a lot of chemical potential disorder. As you can see, the Majorana survives. Some chemical potential disorder still survives. Okay, this is a lot of chemical potential disorder. Majorana doesn't survive. This peak that you see is below the topological quantum phase transition. This beautiful peak has nothing to do with Majorana. This is just, and sometimes you don't see it, as I told you, you don't see it. This is left and this is right from two ends, okay? Left you see it, right you do not. Here right you see it, left you do not. Here left you see it, right you do not, okay? Because this is disorder. This is good with small superconducting disorder. If the disorder is weak, Majorana is stable, as it should be, it's topological. But if disorder is strong, it's not stable. It's a G-factor disorder. So good will be protected against small disorder, but not strong disorder. Strong disorder will produce ugly, and ugly may fool you into thinking that you have seen the Majorana. And I think this is what has happened in all the experiments so far, all the nanowire experiments for sure, and it may very well be all the experiments, period. Right? So again, let me emphasize, this is Nichel, this is Zhang. Okay, retracted now, doesn't matter. Our ugly simulation just disorder produce very good agreement with both. Okay, this is the summary. Doesn't matter before retraction, after retraction. It involves a lot of fine-tuning and post-selection. So do the experiments, okay? This is a very detailed random matrix theory, which I don't have time to describe in details. And you can see this is experiment. This is our theory, and we can reproduce even the magnetic field dependence very well. So, very little stability. One should not call it stable. This is the experiment. One should not call it stable. It reaches some maximum, then comes down, and that is reproduced in the theory. Okay. So most aspects can be reproduced. Now I come to the retracted correct paper where everything is put back. And as I told you, that Leo Cohnhaven found that the lock-in had an error, 10% error. So the peak is actually could be 2.2 instead of 2. Okay. Let me show you the same result from this Frolov-Maurig very bad paper. Okay. This and this are not the same. Okay, I'm sorry. This and this are not the same. This is like nothing. There is no gap in the back at all. Okay. Peak is like 1%. I mean, I just simply did not understand how anybody can claim, even looking at it at loving eyes, that this and this are the same. They're not the same. This is much better data, but it's not quantized at 2 square over h. Okay. And this is our comparison. All right. This is paper, very recent work of Heining Pan, posted. My name is first chair only for cosmetic reason, so that people don't attack Heining Pan. And since I kind of thought this is a very important paper and we should try to reproduce it to the fullest. Okay. All the actual numerical work is Heining. So I want to emphasize that. Okay. We are going alphabetical here, which I do rarely, but here I thought it's important so that people don't get mad at him. So here is our reproduced figure. Look, it looks just like that. Okay, with some fine tuning. This is their experiment, this is our theory. All disorder physics. Okay, there is no topological physics here, all disorder physics, but in the same system. If they can go to higher magnetic field, they're going to see Majorana, provided they can reduce disorder. Okay. And this is how, as a function of Vz, the thing is not stable at all, because this is not a Majorana. This is some disorder-induced peak. So even if you see quantization, suppose, by coincidence, these blue and black lines are also here. Suppose this thing was a bit more broad. Even then, it's not Majorana. Quantization is not the same as Majorana. Quantization is just saying some resistance quantization. Now, if you see quantization all the time, everywhere, well, that will be Majorana. But if you see just once through a lot of post-selection, that's not Majorana. I have emphasized this many times, but it seems people have forgotten this. So this is more theoretical result. This is as a function of barrier height. Again, the peak is not stable. At some value, it's 2 square over h. In general, it's not stable. And this is the breaking up of the wave function, showing why for some fine-tuned position, you could get 2 square over h, because the wave function, many wave functions are overlapping, and in your tunneling measurement, you're picking up, from the tunneling some matrix element, and you can carefully go through it and show that there will be situations where you're going to get some Majorana contribution 2 square over h, but it's really all disorder. So, so in more details with the Delft group, we studied this and we showed when you expect apparent quantization coming from inhomogeneous potential. This is an example of beautiful quantization. Look how beautifully quantized the peak is. Well, beautifully quantized, but these are not Majorana. This is below the topological quantum phase transition. So quantization is not Majorana. This is induced by inhomogeneous potential. Now, the thing continues beyond in the topological regime. But in the topological regime, in fact, the quantization is very bad because you start seeing Majorana oscillations. This is topological regime. You see Majorana oscillation. It's only the trivial regime. You have perfect quantization. So suppose you did this experiment and you saw this. Well, even everybody will admit, even the detractors now will say, oh, this is Majorana, because look at how beautiful the quantization is. Very stable. No, it's not Majorana. It's very stable, but it's very stable for reasons we understand, because of this inhomogeneous potential. It's all worked out in this paper. Okay, we show why this happens and what situations, more importantly, what situations it would happen. Okay, this is when this happens, when the potential is barrier-like. When the potential is barrier-like, you get this very stable, trivial, fake zero bias peak, which are quantized. When the potential is well-like, like this dip, you may get something 2 square over h, but it's very short. It's not very stable. Okay. So if you see something like this, it means you have a barrier-like inhomogeneous potential. Okay. Now with disorder, you get something which is in between the two. It's not as smoothly quantized as this, it's not as sharply quantized as this, but not as narrow and sharp like this. It's like smooth, okay? And this is what is seen most of the experiments now. That's why I personally believe it's all disorder physics. So barrier potential produces stable trivial quantization. Disorder produces trivial ZBCP with 2 square over h with some stability, and well-like potential does not produce 2 square over h. It produces very sharp peaks. Now I'm going to skip these 2 slides because Theodore Stanisky will talk about it, okay? This is very important work, very like 2D force work by Benjamin Woods, graduate student in West Virginia. We collaborate, and realistic 3-dimensional simulation of charge impurities. I think I would not do justice to it since Theodore is talking about it anyway. Let me skip this because I want to spend some time on my next slides, okay? So I apologize. One never knows how fast the talk would go. So I'm going to skip this to Theodore. I'm sure we'll talk about it. So let me just show you 3 of our recent work. This is the 3-terminal. So you say, okay, how can we see Majorana? One possibility is doing 3-terminal non-local measurement. In 3-terminal measurement, you still have 2 leads, but you ground this one, so you can measure all 4 components of your conductance matrix. You can measure the left-left conductance, right-right conductance, which is what I have been talking about. But in addition, you can also measure left-right conductance, this to this, and right-left conductance, this to that, okay? So the non-local conductance can be measured also. What is the advantage? Then you're going to see the zero bias peak in your diagonal conductance. This is from left to left, right to right. But then when you do left to right or right to left, you do not see the zero bias peak, but you see the gap. So in a single experiment, you'll see both the zero bias peak and the gap. And once you do that, Shankar Dasram will give you the award that you saw Majorana. And I would actually, it sounds very vain, but I trust my opinion on whether Majorana has or has not been seen than the rest of the world combined, because I have put more work into it than anybody else. Okay, so you have to convince me, and as Leo once told me, if I'm not persuaded, nobody's going to believe. You see this, I'm persuaded. Okay, do this experiment. The problem is this non-local conductance, the magnitudes are very small. See, it says 10 to the power minus 1, but this is a pristine system. It has no disorder. If you put disorder, these numbers actually become 10 to the power minus 4. The physics remains. You still see some, here is the Majorana peak. You see some Majorana peak, and you see some gap opening here, which can be studied. But your signal has reduced by 4 orders of magnitude. This versus this, that is 10 to the minus 4. So I'm not sure this can be seen. Now, experimentalists tell me, Leo and Charlie both tell me that this can be done, and I'm rooting for them. Okay, this is what disorder system would see. And this experiment, if this can be done, and this is seen, Majorana has been seen. So 3-terminal non-local measurement, see both bulk and boundary. And let me emphasize, topology is a bulk property. Topology is not an end property. So if you want to claim topology, you got to see the gap. There are people who don't understand the physics, think they understand theory, but do not understand theory. Their main vehicle is Twitter. They are saying wrong, dumb things like gap is not important. All they are showing is their ignorance. If you do not see a gap, you have not seen topology, okay? Gap is that hole in the donut. You gotta see the gap, okay? And this experiment can see that, okay? But the disorder is very strong, even stronger, it's not gonna work, okay? This is very recent data. I got it yesterday from Heining Pan, who I think did not sleep for the last week. So I'm gonna show you some order false picture. Experimentalists should stop giving this false color picture. I beg you, please don't give this kind of pictures, okay? I'm sick of these pictures. So much can be hidden. So many almost lies can be promulgated through these pictures by changing color. This picture, you cannot lie, So here is picture, same thing, but cuts. You can see pristine, beautiful gap. This is the aluminum gap. This is the induced gap. Zero field, and then various magnetic fields. Gap is closing. This is a topological on a phase transition point. Then you see beautiful zero bias peak. This is a very long way, 10 micron, 10 times what experimentalists use. Very large, but not unphysically so, spin orbit coupling, and very little disorder, just 0.2 MeV. Chemical potential is 1 MeV. So this is pristine, no disorder. In the presence of disorder here, you see things, you will see it when the disorder is 5 times smaller than the chemical potential. Chemical potential is 1 MeV. Okay, this is larger than the gap. Gap is not the problem. So this is larger than the gap, and you'll still see Majorana. Okay, but this is now disorder equal to the chemical potential. Now you can see there is some problem. So you still see some peak, but then the peak goes away, then it comes back. So if you're stuck in this region, you're not going to see it. Okay, but this is a very long wear and very large spin-orbit coupling. Okay, the spin-orbit coupling is a factor of 5 larger than, and these wears are factor of 10 larger. But even in this system for large disorder, you may lock out and see the Majorana. Okay, if you're unlucky looking here, you would not see it, but you will. But if the disorder is larger, you would not see anything. Okay.
Shankar,
yeah,
there's 10 minutes left.
Okay, I mean, I'm almost done. And this is what happens at finite temperature. Things smooth out, but again, if you're here, you're not going to see anything. Okay. This is for smaller spin-orbit coupling. For smaller spin-orbit coupling, you already have problem. See what happens? Everything goes away because spin-orbit coupling is weaker. Now at this 1 MeV disorder, you're not seeing anything. Exact spin-orbit coupling value, unfortunately, is not known. So if someone can come up with a higher spin-orbit coupling material, that would be very nice. That would really be very nice. Okay, you can see here, same thing, smaller spin-orbit coupling, everything has gone away. Okay, this is a short wear and smaller spin-orbit coupling and large disorder. Now you have nothing, and unfortunately, I think this is what the experiments are now. Okay, unfortunate but true. We have to deal with reality, right? So this is a scary realistic phase diagram. This again came like 2 days ago. So I'm not going to discuss this in great details. This is the magnetic field. This is chemical potential. You see, these are the zero bias peaks of various strength. You can have zero bias peak between any value 0 and 4, including 2. In the non-topological regime, in the topological regime, it's a mess. It's like disorder is producing them everywhere, right? So large zero bias peak, fine-tuned from either end. In short wear, this is all in short wear, okay? Not much hope to see something in short wears. I'm sorry. I'm going to skip this. You will be unhappy, but there is really no time to explain this. This is the claim of seeing, this is the Albrecht experiment claim of seeing exponential protection. Let me just say that we disagree. We think at best what was seen in the unzipped bound state, but I don't have time to discuss this. So let me just conclude by saying what is needed for seeing through Majorana. First, I again emphasize, if you see some quantization once in a while through very careful fine-tuning, it doesn't Majorana. Majorana have not been seen, they will be seen, they most certainly exist. You have to reduce disorder. That's the most important point. I give you a number, Tudor will expand on it. Below 10 to the 15 per cubic centimeter impurities. Okay. Increase measure induced gap, use longer wear, do non-local measurement, bulk opening. No single experiment will suffice. All right, I'll end now. Thank you very much.
Thank you. Yeah, we have time for, I think, a few questions. I think we have a larger number of bigger audience than I thought. So maybe if you raise your hands, I will.
And also, let me just say something. Those who will not get a chance to ask questions, I'll be hanging around here. If you can ask me questions after 6, okay, after 6 p.m., after Tudor's talk. I'm going to stay through all the talks, so I'm just letting you know.
All right. Okay. Yeah. X2, please, Shudang, please go ahead, ask your question. Go ahead. Hold on. Why
I can't hear anything.
Hold on.
Oh,
yeah,
okay. I'm
okay, there you
now
go.
I can hear you. Now I can hear you.
Yeah, go on. Yes.
Yeah. So the question is, clearly you point out that disorder plays a really important role. So
disorder is the whole physics right now. Yeah.
Right. So if I think from a sort of a simple physical, just compare numbers, what are the quantities you are comparing disorder to? Like,
Yeah.
how do I get this 10 to 15?
There are many,
or
many
whatever?
quantities, right? There are many quantities, right? So there is superconducting gap, there is chemical potential, there is Zeeman energy. All of them are important. And this is the problem both in theory and in experiment. And explaining in that will take many days. I emphasize more in this talk disorder with respect to chemical potential, because that's the easiest way to think of a semiconductor compared to Fermi energy, which is the most physical thing. Okay.
But chemical potential is like, okay, so should I think about like addition energy? Like chemical potential is just a number.
No, it has magnitude. What do you mean it's just a number? It has magnitude. It's an MEV. I don't understand what you mean it's just a number. Everything is just a number. Disorder is just a number too. I don't quite understand what you mean.
I guess compared to, for example, the bottom of the conduction band, that's what I always think about.
No,
when I measure the
thing is the chemical.
But this is a mid-gap state.
Hold on. You asked a question, let me answer, okay? I did not understand what you mean by just a number. Yeah, okay. It's a dope material. I mean, it's nothing different. If somebody tells you dope silicon has a chemical potential of 100 MeV, what you think is exactly what you should think here. If somebody says its chemical potential is 1 MeV, except it's a one-dimensional system, nothing is different. It's exactly the same thing. All the energies are factor of 1,000 to 10,000 smaller than three-dimensional bulk dope material. This is the problem. This is why disorder that will be small for a three-dimensional system are gigantic here. Okay. So if your intuition is based on three-dimensional system, this is an unbelievably disordered system. It's the same as what happens in 2D, but here it's even worse because it's 1D. Did I answer your question?
I think so. I think so.
So so all the numbers have to be sub-MeV because the superconducting gap is 100 microvolt. Chemical potential is maybe 1 to 2 millielectron volt. Okay. So disorder has to be smaller than that. And the current samples, mostly disorder is of the order of 10 millielectron volt. Okay.
Okay.
And now you may say, why can't they increase the chemical potential, right? That would be a natural question. Well, you can perhaps, but then you have a next problem that you will occupy many, many 1D subbands. Then your superconducting gap will go down enormously. So you have to hit the sweet spot where your superconducting gap is large. It's not 1 millikelvin, but your chemical potential is not so small. So, it's a very difficult challenge. That's why companies which have $1 trillion work on this problem.
Okay, thanks.
Sure, thanks. Well, Belita Coiler had her hand raised, but then she put it down. Belita, do you still want to ask your question?
Yeah, I thought it would be too late.
No, I think we have a minute or two, yeah.
Shankar, you mentioned you need low disorder. Of course, you mean a better sample of the semiconductor part of the device. Would you suggest other semiconductors that would be?
No. There is no other semiconductor. You need strong spin orbit coupling. Do you know of any semiconductor other than indium arsenide, indium antimonide that has strong spin orbit coupling? I don't.
No, so this is the reason.
You need, Belita, this is what I emphasize, that there are too many constraints here. You need large spin orbit coupling. You need large G factor, because if you do not have large G factor, you have to apply like a 10 Tesla field.
Okay.
So I don't know any, and this is the number. I gave you the number. Reduced disorder below 10^15 per cubic centimeter. I mean, we are putting our money where our mouth is. We did a lot of very hard calculations to come up with this number. Now you may say, how does this number compare with best gallium arsenide? Lauren Pfeiffer's gallium arsenide? He has this number down to 10^12 in best quality gallium arsenide. Best quality silicon, this number is 10^13. So this has been achieved in other semiconductors, but not in indium antimonide and indium arsenide, where this number is currently maybe 10^16. But this can be done. This is not an undoable problem, right? This can be done. LIGO, they reduce noise to C, right? BEC, they reduce temperature to C. This is a doable problem. The target is not. If this number is 10^1, you'd say that's impossible. But this 10^15 per cubic centimeter, I'm giving you the number.
Okay, thank you.
Okay, so excellent. Sorry, there's one more question, but I think we're out of time. We're hitting up against.
Email me the question. Whoever it is, email me the question. I'll send a response. Okay.
All right. So let's thank Shankar for a wonderful talk. Shankar, can you stop sharing now so that?
Yes, I'm going to stop sharing right now.
Okay.
Okay, it didn't stop. I have to figure out how to stop.
Oh, and I will actually.
You can unshare me. Actually.
Oh yeah, I think.
I don't think I can unshare myself.
So I'll pause recording for a quick second. No, actually.
No. You can. There is stop share. I found it. Stop share. I'm gone.
Okay, good. So yeah. So Professor Machida, can you start sharing?
Yes, sure. Can you see my slide?
You're starting. Yes, we can see your screen. Wonderful.
Yes, I will start slideshow mode.
Okay. So yeah, I'll just our next speaker is going to be Professor Machida from RIKEN, and he's going to tell us about another very fascinating platform that Shankar alluded to briefly, which is these iron-based superconductors, which have had, I would think, some pretty amazing progress. So, Professor Machida.
Yeah, thank you for the introduction. I'm Tadashi Machida from the RIKEN in Japan. First of all, I'd like to appreciate Professor Shankar Sarma for giving me very nice opportunity to talk about science results in this very interesting conference and for organizing this very interesting Majorana-related conference. So today I'm going to talk about the searching for the Majorana quasi-particles in the iron-based superconductors, selenium-doped iron telluride by using the ultra-low temperature dilution refrigerator STM. So first of all, I'd like to introduce my collaborators as shown here. The top panel indicates my group members, and then Dr. Tetsuo Naguri is the PI of my group, and all of them provide who help and advises in the STM measurements and in analyzing the STM results. And Professor Tamegai's group in the University of Tokyo, and Dr. Sun in the Yamagakuin University, and Professor Sasagawa group in the Tokyo Institute of Technologies provide the high quality single crystals of the selenium-doped iron telluride used in this work. And also the Dr. Chinkei Chu, he is now in RIKEN. He actually provides critical theoretical help in explaining our experimental results. Okay, so this is the outline of my talk. First of all, I would like to briefly introduce the previous STM works for detecting the Majorana quasi-particle in the topological superconductor candidate systems. And then after that, I would like to show you our recent efforts to detect the Majorana quasi-particle in the topological superconductors, including the development of the ultra-low temperature STM and the observation of the zero energy peak around the vortex core of the selenium-doped iron telluride, which is one of the iron-based superconductors. And then I would like to also show that electronic states around the excess iron impurities in this selenium-doped iron telluride, where the Majorana zero mode has been theoretically predicted recently. And finally, I would like to summarize my talk. Okay, so let me show you my brief introduction of my talk. Maybe you know that it is very important to realize the topological superconductivity, of course, as a platform for the Majorana quasi-particles. One of the promising ways to realize the topological superconductivity is that the opening of the superconducting gap on the spin polarized topological surface states by using the proximity effect from the conventional superconductors, which is originally proposed by the Professor Fung and Ken about 10 years ago. And then by using these very nice ideas, the several candidate systems for the chiral P-wave topological superconductivity has been proposed as shown here. For example, the Rashba semiconductor nanowires put it on the S-wave superconductors, and also the ferromagnetic atomic chains on the S-wave superconductors, and also the heterostructures between the topological insulators and conventional superconductors as shown here like that. In addition to these artificial structures, it has been also proposed that the S-wave superconductors with the topological surface states is expected to be the one of the candidate system for the topological superconductors. So in this system, we have the topological spin polarized topological surface state as shown here on the surface of this material. And then the bulk is superconducting. So because of the proximity effect from the bulk superconductivity, the superconducting gap opens even on the topological surface state as shown here, which gives rise to the current P-wave topological superconductivity. The selenium doped iron telluride is our target material in this work. That is belonging to this class of material. So anyway, in these candidate systems, there are many experimental works to trying to detect the signature of the Majorana quartz particles. One of the most intriguing example of such measurements is the SDL measurements on these topological superconductor candidate systems. Actually, we can see the clear zero energy peak in the tunneling spectrum taken at these edges and the vortex core of these candidate systems. However, it has been still controversial whether the observed zero energy peak really originates from the Majorana zero mode or not. So because that conventional bound states can appear around zero energies. So therefore, we have to distinguish between the Majorana zero mode and the conventional bound states to affirm the observed zero energy peak really originates from the Majorana zero mode. From this point of view, the tunneling measurements around the vortex core is somewhat beneficial because conventional energy levels of the conventional vortex bound states has been already established. In other words, we can estimate the energy levels of the conventional vortex bound states if we know the superconducting gap size and the Fermi energies of our target material before the measurements. So this is a schematic energy diagram of the vortex bound states expected in the chiral P-wave topological superconductors. Now, of course, we have the Majorana zero mode at the exactly zero energy, as shown here, as shown by these red balls. And also, in addition to this Majorana zero mode, we also have the conventional vortex bound states, which is called as the Carolido-Jan Maturicon states, as shown by these yellow lines. The most intriguing parameters to distinguish between the Majorana zero mode and the trivial vortex bound states is that this energy separation, which depends on the Fermi energies of the materials and the superconducting gap of the material. Unfortunately, in the usual superconductors, this energy separation is quite small. That is less than 1 microelectron volt. Because in the usual superconductors, this Fermi energy is order of the electron volt. On the other hand, this superconducting gap is less than 1 millielectron volt. So therefore, this energy separation is quite small, less than 1 microelectron. So which cannot be resolved even by using the recent technology of the SDR. So therefore, we have to choose the proper material to distinguish between the Majorana zero mode and the trivial vortex bound states. The material should have the a large energy separation of this large energy separation, and the materials also should have the topologically non-trivial nature, shown like that. The selenium doped iron telluride is one of the suitable material for that purpose, because this material has a relatively large superconducting gap that is about 2 millielectron volt, and also the very small Fermi energies that is about 10 to 20 millielectron volt. So from these parameters, we can, of course, calculate the effective expected energy separation between these bound states to be about 100 to 200 microelectron volt. And that is acceptable for the SDM measurements. Okay. Therefore, the second requirement, the the tellurium substitution is a very intriguing parameters to make the system the topologically not trivial. So here is a band structure calculation results of the pristine iron selenide and the selenium doped iron telluride. Okay. Of course, the selenium pristine iron selenide is the topologically trivial material. If we substitute the tellurium, this tellurium substitution enhances the coupling between the PZ orbital of the chalcogen atoms, as shown here. So because of this enhancement of the coupling between the PZ orbital, these bands associated with the PZ orbital becomes more dispersive. And then this energy level goes to the Fermi level like that. And then as a result, this PZ band crosses with the pre-existing D bands of the iron atoms. And then furthermore, the tellurium substitution, of course, also enhances the spin orbit coupling, which gives rise to the band inversion around this crossing point. So therefore, this material is topologically non-trivial. Actually, the recent spin-resolved RPS measurements clearly indicates the spin polarized Dirac cone on the surface of this material. And also, RPS also indicates the opening of the superconducting gap on this spin polarized Fermi surface, suggesting that the chiral P-wave topological superconductivity is expected to be realized on the surface of this material. So because of this topological nature and the very large energy separation between the both expand states, this material is expected to be suitable for the detecting the Majorana zero mode around the vortex core of the topological superconductors. So because of this reason, there has been two STM works before our measurements, investigating the electronic states around the vortex core in the selenium doped iron telluride. The first paper indicates that there is a zero energy peak, suggesting the existence of the Majorana zero mode around the vortex core. And on the other hand, the second paper indicates that there is no zero energy peak. And also there are only the finite energy peaks originating from the conventional vortex bound states, as shown like that. So as you can see, the conclusion of these two papers are totally different with each other. So when I saw these two papers, I was wondering that the energy resolution of these their experiments is not enough to distinguish between the Majorana zero mode and the conventional vortex bound states. Because their energy resolution is about 250 microelectron volt. And that is comparable with or larger than the expected energy separation between the Majorana zero mode and the trivial vortex bound states. And also, I was also wondering that there may be another hidden factors governing the emergence of the zero energy peak around the vortex core of this material. So maybe we needed to the more systematic measurements around the vortex core of this material with much better energy resolution. To do this, we constructed the ultra-low temperature dilution refrigerator SDM, as shown here, which has the capability to do the very stable spectroscopic imaging measurements under the ultra-high magnetic field of 17.5 Tesla and the ultra-low temperature of 90 millikelvin. The corresponding energy resolution is about 20 microelectron volt. Okay. So thanks to this high energy resolution of this SDM, we can obtain a very nice BCS-like superconducting gap with a very sharp coherence peak, even on this low temperature superconductor, low TC superconductor aluminum. So by the way, by using this high energy resolution SDM, we have re-investigated the electrolytic states around the vortex core of the selenium doped iron telluride. So before showing the experimental results and the magnetic field, I'd like to show you how disordered this material is even without magnetic field. Okay, so this is a typical topographic SDM image taken on the cleaved surface of the selenium doped iron telluride on the 187 nanometer square field of view. We can see the very flat, atomically flat surface without any excess iron impurities. Okay, so and then if we magnify the one of the very small area, we can see the square lattice structures composed of the topmost carbon atoms. In this case, the carbon atoms are the selenium or tellurium. The ionic radius of the selenium is smaller than that of the tellurium. Therefore, we can identify the location of the selenium and tellurium as shown here by using this topographic information. And then, of course, we can also map out the local selenium densities or the local chemical compositions as shown here. We can see the local selenium density is somewhat disordered like that. Okay, so next, let me show you the disorders in the electronic states and at the magnetic field, at the zero magnetic field. So this is a tungsten spectrum taken at the zero magnetic field at the lowest temperature of 90 millikelvin. Then we can see the fully gapped structures along with multiple peak structures above the 1.5 millielectron volt, as shown here like that. So this multiple, one of the origin of the this multiple peak structures is that the existence of the multiple superconducting gap due to the multi-band nature of this material. However, the number of these peaks exceeds the number of the bands. So therefore, we need another factors to explain these multi-peak structures. Anyway, this superconducting gap spectrum is very complex in this material. And then to further investigate the spatial variation of these superconducting states, we take the line profile of the tungsten spectrum as shown here. We can see the very complex spatial variation of the superconducting states as shown by these red boxes like that. And then if we map out the local superconducting gap size as shown here, we can also confirm the very disordered states of the superconducting states. Yeah, like that. And then if we take a look at carefully within the superconducting states, superconducting gap, we found some pairs of the peaks within the superconducting gap, as shown by these orange arrows. To visualize the spatial distribution of these in-gap states, we mapped out the energy integrated local density of states within the superconducting gap, as shown here like that. So as you can see, there are many localized features, which is randomly distributed. And then because of this localized nature of these in-gap states, it is conceivable that these in-gap states maybe originates from the impurities or defects existing inside the sample. So anyway, not only the chemical composition, but also the electronic states are strongly disordered in this system. Okay, so even without magnetic field. So next, let me show you our experimental results under the magnetic field. Now, here is a typical zero-bias conductance map taken at 1 Tesla. And on the exactly same field of view as those in the images as shown before, we can see the totally 18 vortices in this field of view, okay, as a bright spot. For example, here and here and here. And then, first of all, we focus on these two vortices and the tungsten spectrum as shown here like that. In both graphs, this gray line indicates the tungsten spectrum taken at the 0 Tesla at the exactly same location of the vortex core. Okay. In both vortex core, we can see the many peak structures induced within the superconducting gap, as shown here and here. Okay. And then by considering there is no features within the superconducting gap at the zero magnetic field, these induced vortex-induced peaks originates from the vortex bound state. And if we magnify just around the Fermi level, as shown here, the multiple peak structures becomes more recognizable like that. That most importantly, at this vortex core, we can see the clear zero energy peak within our experimental resolution, along with the conventional vortex bound states appearing at the finite energies shown here like that. And then if we move on to the neighboring vortex core, this vortex core, we can, unfortunately, we cannot see any feature of the zero energy peak shown like that. There only the finite energy peaks originates from the conventional vortex bound states. Okay, so these two results clearly indicates that there are two kinds of the vortices in this material. The one has a zero energy peak. The other one doesn't have the zero energy peak. And also these results gives rise to one question. What governs the emergence of the zero energy peak or disappearance of the zero energy peak? The one of the candidates to answer this question is that the chemical and electronic disorders pre-existing even without magnetic field. For example, the local seismic densities and the homogeneity of the superconducting gap and distribution of the defects or impurities. To investigate the spatial correlation between the local emergence of the zero energy peak and these three local quantities, we superimpose a location of the vortices with and without zero energy peak, as shown here like this. However, we cannot see any spatial correlation between these three maps and the local emergence of the zero energy peak, as shown here. So therefore, this means that at least these three local quantities are not main player for the local emergence of the zero energy peak around the vortex core. However, it is also possible to think that another local parameters governs the emergence of the local emergence of the zero energy peak. To test these possibilities, we compare the vortices showing the same location at the different magnetic field. So these four vortices marked by the light blue circles in these images are such a vortices sharing the same location at the 1 Tesla and 3 Tesla. For example, this vortex corresponds to this vortex corresponds to this vortex. And then these are the corresponding tunnel spectrum taken at 1 Tesla and 3 Tesla at these vortex cores. Okay. For example, in this vortex core at 1 Tesla, we can see the clear zero energy peak. However, at the 3 Tesla, this zero energy peak is gone, even though these two tunnel spectrum taken at the same location. If the local emergence of the zero energy peak originates from only some local quantities, the tunnel spectrum taken at the same location should be the same. However, the actual experimental results are not the case. So therefore, we safely conclude that any local parameters are not main player for the local emergence of the zero energy peak around the vortex core. And then these experimental results also suggest another possibility that the magnetic field strength itself may play an important role for the emergence of the zero energy peak. So to test these possibilities, we performed systematic magnetic field dependence measurements as shown here like that. So these are the zero bias conductance map taken on the exactly same field of view at the different magnetic field from the 1 Tesla and 3 Tesla to 6 Tesla. Okay. Now, of course, if we increase the magnetic field, the number of the vortices linearly increases. And to investigate which vortices show the zero energy peak, we took the tunneling spectrum at all of the vortex core in this field of view from the 1 Tesla to 6 Tesla. There are actually 222 vortices there, but I took the tunneling spectrum at all of the vortex cores. And then from all of the tunneling spectrum, obtained tunneling spectrum, we made a histogram of the appearance probability of the peaks at the given energies, shown here like that. So for example, the value at zero energy in this histogram, is that how many vortices shows a zero energy peak in this field of view. For example, at 1 Tesla, this value is about 80%. So this means that the 80% of vortices shows a zero energy peak in this field of view at 1 Tesla. And then surprisingly, this value, the fraction of the vortices with the zero energy peak, systematically decreases with increasing the external magnetic field, like that. So to check the reproducibility of this magnetic field dependence of the zero bias peak, we repeated the same experiments on another field of view, like that. Very fortunately, we can see that a very similar magnetic field dependence of the zero energy peak as shown here. And also very fortunately for me, the similar magnetic field dependence of the zero energy peak has been reported after this work from the other groups. So this means that the observed magnetic field dependence of the zero energy peak is a true nature in this material. So, and then when I saw this magnetic field dependence of the zero energy peak, I was wondering how can we explain the magnetic field dependence of the zero energy peak, even if we assume the observed zero energy peak originates from the Majorana zero mode. The one of possible explanation is the splitting of the Majorana zero mode due to the hybridization between the Majorana quasi-particles. Because the average distance between the vortices should decrease with increasing the external magnetic field. So which gives rise to the enhancement of the hybridization between the Majorana quasi-particles. Okay. According to the recent theories, in the uniform vortex lattice, the Majorana hybridization splits the Majorana zero mode at all of the vortex cores. In such a situation, all the vortex core doesn't show the zero energy peak. However, this is inconsistent with our experimental observations, showing the finite fraction of the vortices shows the zero energy peak even at the higher magnetic field, shown here like that. So therefore, to explain these experimental observations, we need another practice in addition to the hybridization between the Majorana quasi-particles. Okay, so if we take a look at that carefully, observed this vortex arrangement, the vortex arrangement in all of the magnetic field is quite disordered, especially for the higher magnetic field. So therefore, we speculate that not only the hybridization between the Majorana quasi-particles, but also the disordered arrangement of vortex core are also important factors to explain our experimental results. To check these speculations, my theoretical colleague, Dr. Chin-Kai Chu, theoretically investigated the effect of the interaction among the multiple Majorana quasi-particles in the disordered vortex lattice systems in the chiral P-wave topological superconductors. He actually calculated the local density of the states at all of the vortex cores that he considered. And then he counted how many vortices shows the zero energy peak at the many magnetic field strengths. And then he directly compared his calculation results with our experimental results shown in this graph. So in this graph, the red dots indicates that our experimental results, and green and blue dots indicates his calculation results. As you can see, we can see the good agreement between the experiments and theory. So this agreement between the theory and the experiments suggests that we can explain our observations of the magnetic field dependence of the zero energy peak by considering the interaction among the Majorana particles in the disordered vortex lattices. even if we assume the zero energy peak originates from the Majorana particle. Now, however, the zero energy peak, observed zero energy peak is just one of the necessary conditions, but is not the sufficient condition to prove the existence of the Majorana zero mode. So therefore, we need to capture the another features associated with the Majorana quasi-particle to prove the existence of the Majorana zero mode. So the one of the such features of the Majorana zero mode is the quantization of the zero energy peak, zero bias conductance, which independent of the tunneling barrier strengths at the low temperature limit. Okay. So in principle, we can test this kind of phenomena by just measuring the zero bias conductance as a function of the tip sample distance, shown here like that. This tip sample distance dependence of the zero bias conductance has been already investigated around the vortex core of the selenium doped iron telluride, as shown in these papers. Which comes from the Professor Condensed group. They claim that the zero bias peak around the vortex core start to saturate at a particular tunneling strength, and then it shows the plateau-like behaviors. According to these papers, this plateau-like behavior endure the observed zero energy peak originates from the Majorana zero mode. To check the reproducibility of this phenomena, we also performed the similar experiments as shown here like that. So these are the tunneling spectrum as a function of the distance between the tip and samples, taken at one of the vortex core showing the zero energy peak. And then we extracted the absolute value of the conductance of this zero energy peak and plot them as a function of the distance between the tip and sample, as shown by these orange lines. At first glance, we can see the plateau-like behaviors as shown in the previous measurements. So basically, our results are consistent with the previous SDM measurements. However, as shown in the previous talk given by the Professor Sarma, this kind of plateau-like behavior is not the Majorana zero mode. So we need to say the observed zero energy peak originates from the Majorana zero mode. We need another smoking gun evidence to prove the existence of the Majorana zero mode. So I think, in my opinion, there is no smoking gun evidence at this moment to prove the existence of the Majorana zero mode around the vortex core of the selenium doped iron telluride. So all of the observed features associated with the zero energy peak is that just a necessary condition. It's not a sufficient condition. Okay. Okay, so next, let me move on to the next topic associated with the electronic states around the excess iron impurities shown here, where the Majorana zero mode has been theoretically predicted recently. So the first suggestion of the existence of the Majorana zero mode has been made in these tunneling measurements. Showing the clear zero energy peak around the vortex around the excess iron impurities, as shown here like that. Now, after these measurements, it has been theoretically predicted. I'm sorry, it has been theoretically predicted the Majorana particle can appear around the excess iron impurities when the two of the excess iron impurities form the vortex and anti-vortex pairs, which is called as the quantum anomalous vortex core. Now, however, of course, we can also expect the conventional U-Shiba-Rushnov states around these excess iron impurities, because these excess iron impurities work as the magnetic impurities in the superconductors. So therefore, we have to distinguish again between the Majorana zero mode and the conventional U-Shiba Rushnikoff states. However, the energy solution in the first STM experiments is about 600 microelectron volt. It's not enough to distinguish between this Majorana zero mode and the U-Shiba Rushnikoff states. So therefore, we have to we need a much better energy solution, and then we investigated the electronic states around the excess iron impurities. Okay, so this is a typical STM topographic image taken on the acrylic surface of the one of the selenium doped iron telluride single crystals. Sometimes we encounter such a surface containing several number of the excess iron impurities on the surface, as shown by these bright dots. To investigate whether the zero energy peak really exists or not in all of these excess iron impurities, we took the tunneling spectrum on all of the excess iron impurities, as shown here like that. So we can see that the reverse peak in only these three excess iron impurities, like that. And then on the other hand, we cannot see any features of the zero energy peak in most of the excess iron impurities. But there are only the finite energy peaks in most of the excess iron impurities. So this means that in most of these excess iron impurities only has the U-Shiba Rushnikoff states, conventional U-Shiba Rushnikoff states. But doesn't have the Majorana zero mode around the excess iron impurities. Therefore, the remaining problem is that whether the observed zero energy peak in these three excess iron impurities originates from the Majorana zero mode or not. Okay, so to test this, we have performed two kinds of experiments. The first one is the measurements of the spatial dependence of the tunneling spectrum around the excess iron impurities. So if the observed zero energy peak originates from the Majorana zero mode, this peak stays always the zero energies, even when we move away from the excess impurity site. So this is our experimental results of the line profile of the tunneling spectrum along this arrow crossing the excess iron impurities. At the excess iron impurity site, we can see the very clear zero energy peak. But when we go away from the impurity site, this zero energy peak split into the two finite energy peaks, as shown here like that. And also along this direction, we can see the same features. When we go away from the impurities, this zero energy peak split into the two finite energy peaks like that. So this means that the observed zero energy peak is not the Majorana zero mode, just the U-Shiba Rushnikoff state. Okay, so second, another most important test to distinguish between the U-Shiba Rushnikoff states and the Majorana zero mode is that tip height dependence of the tunneling spectrum. As shown here, the magnetic impurities underneath the alpha tunneling tip always experiences this Lennard-Jones-like atomic force from the STM tip. So therefore, when we approach the tip to the magnetic impurities, the vertical location of these magnetic impurities should change following this Lennard-Jones-like potential. Okay, and then this changing in the vertical location of the magnetic impurities also change the effective exchange coupling between the magnetic impurities and the electrons of the Cooper pairs. Since the energy levels of the U-Shiba Rushnikoff states depends on this exchange coupling, therefore, when we change the distance between the tip and magnetic impurities, of course, the U-Shiba Rushnikoff states also varies as a function of the distance between the tip and magnetic impurities. So this tip height dependence of the U-Shiba Rushinov states has been already observed in the conventional superconductors around magnetic impurities. So in these measurements, this author of this paper used the superconducting tip to improve the experimental energy resolution. So therefore, the actual zero energies of the sample is offset by the superconducting gap size of the STM tip, as shown by these gray lines. So these gray lines corresponds to the actual zero energies of the sample. And then when we approach the tip to the magnetic impurities, this U-Shiba Rushinov state first goes to the zero energies, and then split into the finite energies again, and then it goes to the zero energies again. Okay. So anyway, so the energies of the U-Shiba Rushinov state strongly depends on the tip height. Okay, distance between the tip and magnetic impurities. So therefore, it is conceivable that this tip height dependence of the U-Shiba Rushinov state can be used for testing whether the observed zero energy peak originates from the Majorana zero mode or not. Okay, so this is our experimental results of the toning spectrum as a function of the relative distance between the tip and excess iron impurities. At this tip height here, we can see the clear zero energy peak as shown in this orange spectrum. And then when we approach the tip to the excess iron side, this zero energy peak split into the two finite energy peaks as shown here like that. So this splitting suggests that the observed zero energy peak is not the Majorana zero mode. It's just a U-Shiba Rushinov states, conventional U-Shiba Rushinov states. So from all of these experiments, we safely conclude that the excess iron impurities in the selenium doped iron telluride works as the conventional magnetic impurities in the superconductors. And then it only has the conventional U-Shiba Rushinov states, but it doesn't have the Majorana zero mode. Okay. Okay, so maybe, okay. So this is summary of my talk. To detect the Majorana quasi-particles in the topological superconductors, we have constructed the ultra-low temperature dilution refrigerator STM that has the capability to do very stable spectroscopic imaging measurements with the ultra-high energy resolution of about 20 microelectron volt. And then by using this dilution refrigerator STM, we have performed the STM experiments around the vortex core of the selenium doped iron telluride. And then we observed the zero energy peak around the vortex core in this material. And also, we also found that the coexistence of the two kinds of the vortices, one has a zero energy peak, the other one doesn't have the zero energy peak. And from the systematic measurements by using this STM, we also found that the fraction of the vortices with the zero energy peak systematically decreases with increasing the external magnetic field. And then thanks to the theoretical help from Dr. Jinkei Chu, we can explain the observed magnetic field dependence of the zero energy peak by considering the effect of the interaction among the Majorana particles in the disordered vortex arrangement in the vortex lattice. So, however, as I say, the observed zero energy peak is just one of the necessary conditions, is not the sufficient condition. So we need another smoking gun evidence to say the observed zero energy peak originates from the Majorana zero mode around the vortex core of the selenium doped iron telluride. And then, and furthermore, we also investigated the electronic states around excess iron impurities in this selenium doped iron telluride. And then from our results, we conclude that the excess iron impurities works as the conventional magnetic impurities in the superconductors. And then it only has the U-Shiba-Rushnov states, conventional U-Shiba-Rushnov states, but it doesn't have the Majorana zero bond around the excess irons. Okay, so as a future work, I think we have to think about what is the smoking gun experiments. And then, and also we have to think about how to control the Majorana quasi-particle as the next step. Okay, so maybe time is up. Thank you for your attention.
Thank you very much for an excellent talk.
Thank you.
Yeah, and also for leaving lots of time for questions. This is wonderful. So actually being chair, I'll take advantage of that and ask the first question. So this is about the quantization. So you showed figure 2 from the Zhu et al. Science paper from Hong Ding's group.
Yes, just go back to the, yes, maybe this is slide, right? Okay, this slide,
no,
right?
the
Okay.
one which had a plateau.
Yeah.
But the plateau was near half.
Yeah, sure.
Right.
Sure.
Exactly, excellent.
Mm.
So they also have figure 3, where this plateau is claimed to be basically at 2e squared by h. So which is so that's the one that I found very intriguing, and I was wondering what your opinion was, because it seems like you were not able to reproduce that. That was not. You've seen plateaus that are consistent with this figure 2, but not figure 3.
Figure 2 means, I'm sorry, I don't understand figure 2. Figure 2 in the science papers, right?
Yes, figure 2 in the science. This is figure 2 in the science paper, but figure 3 in the science paper has like the same as panel F that you show here, but the dashed line is basically at 2e squared by h. Much closer actually than the other.
I see. I don't remember precisely, but this figure shows the Plato value. This figure shows the data after the deconvolution of the finite temperature problem. I think I remember that. So that is why that value exceeds, reaches to the quantized value 2e squared by h.
Anyway, we should discuss this later, because I actually studied this paper a lot carefully. There was an issue where the first version of this paper on the archive did not, actually even the archive version even now does not have that plot. It only has a deconvolved plot, but I think this one is. So to me, at least, this is a very important plot. Okay, if what you said is true, that this just deconvolution, then of course it doesn't matter. But if it's actually 2e squared by h, to me that's that puts iron superconductor sort of ahead Majorana nanowires right now. So it's a very important issue to sort of resolve and reproduce.
I think so.
Okay. And maybe one quick question before I move on. So you showed 1 Tesla and had 80% Majoranas. What about lower magnetic fields for the fixed light?
I did, but the different single crystal. In this experiment and the 0.5 Tesla, we had nearly 100% both fields show the zero as a peak.
I see. Excellent. Okay.
Thank you for the question.
Sure, absolutely. Maybe next question.
Could I ask a question?
Yes, please do.
So first, I want to applaud you. Very, very nice talk, and exactly what I wanted. Okay.
Thank you very much. Thank you very much.
A lot of information with no big claim, and everything to the point. I enjoyed your talk enormously. I have 2 informational questions. Question number 1: in this paper, Science Advance, that you wrote with Chinkai sent a copy, but I have to apologize. I didn't read it. You use the word interaction. It's the same. It's just overlap you're talking about, right? Overlap in a lattice. There is no real interaction, right? It's still the overlap of the Majorana wave function in a lattice, relaxed lattice, glassy lattice, right? The word interaction means different things. When you say interaction, you still mean just wave function overlap, right?
Yeah. So I don't understand the theoretical framework correctly, precisely, but in my understanding, the key point is that the effect of the superconducting phase in the third vortex core to the wave function hybridization of between the 1 and 2.
Good. Understood. Second is a question that you alluded to at the end of your talk, but you did not elaborate. And this is a question I discussed a lot, even before Jaideep saw, with Sumanta Tiwari. I don't know if he's in the audience or not. When we thought a lot about Swanson-Rutherford, I think with Jaideep, we talked about in 2D system. Suppose you have Majorana here. It looks, very tantalizing, right? Suppose you have Majorana. How do you do braiding? How are you going to move the Majorana around? I mean, I'm sure you've thought about it.
That's good question associated with my future work. My future work of the yes. So one of the possible way to control the Majorana in real space is the using of the magnetic tape. If we use a magnetic tape.
Magnetic tape, you said?
Yeah.
I didn't understand.
Yes, magnetic tape. Magnetic STM tape. If we use a magnetic tape, of course, we can control the vortex itself by using the magnetic interaction between the tip and magnetic vortices.
Okay. Yeah, I mean, we, in our Swanson-Rutherford paper, we said one should use an AFM tip to move the vortex around. Okay.
Yeah.
But you want to do a magnetic tip. Okay. So you think it's something very difficult, but you think it can be tried at least to see if the vortex can be moved around with a magnetic tip, right? Experimentally, it's something you can try.
Yeah, in principle, it's possible, but I think it's quite difficult to keep the one vortex at the same location. When we move the vortex core to the another vortex core, maybe some interaction, magnetic interaction between the vortices play an important role. So it's quite difficult.
Yeah, this is an open question. We should think about
it. We have to think about that kind of interaction between the vortices to control the vortex.
Okay, thank you. I'm done.
Yeah. Thank you for the question.
Okay, if there are other questions, please raise your hands. Or I mean, you can start speaking, but I think we still have a large number, so I would prefer if someone just raises their hands and to ask a question.
Jaideep, can I ask a question?
Oh, yeah, okay, Shumanta, go on. Yes.
So Professor Machida, that was a wonderful talk, but I have two questions. One on one of your plots where you showed those zero energy peaks, and then there are a number of finite energy peaks as well. Can you show one of those?
I'm sorry. So speak again. I can't hear you. So
can you hear me now?
So, yes, now.
Okay. Yeah, in some of your plots, you showed some zero energy peaks and along with it, some finite energy peaks as well. And I seem to remember that there was a strong particle-hole asymmetry in those plots.
You mean the particle-hole asymmetry between this one and this one?
Yeah, exactly. So
that's a really good question. So according to the because they are the Bogoliubov quartz particle excitation, right? So therefore, this wave function follows these equations. This means that the particle-hole-like excitation, summation of the particle-hole-like excitation, the particle-like excitation and hole-like excitation is always 1. Okay, so this means that the allocation at the location where the hole-like excitation is dominant, the electron-like excitation should be small. So because of this relationship, we can expect this particle-hole asymmetry of the intensity of the conventional vortex bound states. Actually, some simulations associated with the trivial vortex bound states in the conventional superconductors also shows that this kind of particle asymmetry of its intensities. So this is a very
So
simple.
this has been seen then, you're saying that this has been seen in other older experiments, for instance, where they found just the colloid and matrix states and no zero. So they did see similar particle hole asymmetry there as well?
No, you mean that so this kind of the particle hole asymmetry in the intensity can be observed in the older trivial superconductors or not, right?
Yeah,
it's your question, right? So no, actually no. So because the reason why this reason comes from the very small energy separation between these bound states in the usual superconductors. So it cannot be distinguished even by using the ultra low temperature STR.
I see. So that brings me to my next question. If I can have one more, or maybe half a more minute. So typically, as you said, in trivial superconductors, the scale delta square by EF is very, very small.
Yeah, sure.
And that has to do with the fact that EF is large and delta is small. But here you are saying that delta is reasonably large, but EF is small. That, I mean, I have heard these before, but why is that? I mean, if EF is small, that already tells you that the electron density is small.
Yeah, sure.
That should reduce delta even further.
You mean okay? So this material.
So why are they going in opposite direction? That the delta is large.
Yeah. That's good question. Yeah, that's good question. This material is not a single band material. It's a multi-band material. The two small hole-like pocket and two small electron-like pocket. So then it's not a conventional. Yeah, it's not a conventional superconductors. So that is why we can obtain the high TC.
Actually in the lower bands, and they are the ones who are producing the superconductivity.
Yeah.
All right. And thank you. That was the end of my question.
Yeah. You're welcome.
Hi, Jay. Can I ask a question?
Oh yeah, please, Roshan, go ahead.
Thank you, Dr. Machida. It's a really wonderful talk, and I especially enjoy the last part on the Yoshiba state because that actually puzzled me for quite a while. And actually, this is, I think it clarifies a lot of things happening in this field, right? Because people are claiming that it's Majorana. And actually, I actually have a question about the vortex physics here. So since you have like a pretty comprehensive statistics about which one vortex shows zero bias peak and which one is not, I'm just wondering because I think practically if you want to hybridize this Majorana to make some trivial, I think we actually need an even number of Majorana being hybridized, right? So the question I think I have is when you actually try to sort out which Majorana has a zero bias peak and which one does not, are they actually come in pairs? So basically, for each for a trivial vortex, do you always find that there is a neighboring another trivial vortex that accommodate that one?
Yes, that's a good point. You mean that the zero bias peak vortices should form the pairs because the Majorana always come in pairs, right?
I think my question is
like that, right?
I think my question is if you just look at the top surface, right? You have these trivial vortices. Do they always come in even numbers, right? Because if you want to hybridize three vortices, then you're always left with the one zero bias peak.
So in principle, we cannot check the zero bias peak, the number of the vortices of the zero bias peak even or not. We cannot identify the parity of the number of the zero bias peak vortices because
Okay, I think my maybe let me rephrase my question. Just sorry about that. I think because now you have like a triangular lattice, vortex lattice, right? The upgrade lattice on the surface. That's basically. And my question is for example, if you see a trivial vortex at one lattice point, for example, in the 1 Tesla plot at the center, if we
what do you mean the trivial vortex, right?
the one
without
without the
zero
third
peak.
Yeah,
Okay,
yes, yes. And do all the 6 neighbors also show? So basically, in this case, I think my question is like, once you see a trivial vortex, right, sitting in the middle of that triangular lattice.
Okay, that's a good question. I did such kind of the analysis. Where is my slide? Okay, this one. Okay, you see here, right? So this is a analysis of the Voronoi analysis. The orange one indicates vortices with zero energy peak, right? Okay. So, however, this one has a zero energy peak, but the neighboring vortices like that. So these are the vortices with the zero energy peak, and these are the doesn't have the zero energy peak. Okay. So it's very complex. We cannot see any systematic behaviors about that.
Okay, thank you.
Yeah.
Excellent. I think that is all the time we have now. Thanks very much for a wonderful talk and wonderful question session. I'll pass the baton on to Yangzi, who I think will turn on and off the recording or something. But anyway, Yangzi, it's up to you now.
Thank you. I will stop sharing.